Now let's look at the topic of testing. The first question is, why should code be tested, right? We have presumably written code, and you could argue that the testing is in the process of actually running the code itself. But that's usually too late to catch bugs. You don't want to catch bugs when they are actually out there in the field and your code is running. So why should it be tested? You want to test for basic functionality. You also want to make sure that even if certain kinds of corner cases, maybe extreme environments, a temperature that you never really anticipated to start with, right? Or some kind of uncertainty in the inputs, some strange behavior that was not expected to happen. If any one of those happens, can you sort of still say how your program will behave? And do you have a definition of correct behavior, and does your program ensure correctness of the behavior, right? So all of this basically tells you why you would want to test the code in the first place, and what we are now interested in is how would you go about testing the code and what parts of this can be automated, because anything where you need to sort of manually sit and uh, check each part of the code is by itself going to be error prone in some ways. So an example of the basic kind of test is what's called a unit test, right? Unit tests basically say that each function is tested as a separate unit, right? And ideally you should write the tests before writing the function. This is sometimes also referred to in the software engineering area as test driven development. Even if you don't go down the full path of test driven development, the basic idea that you have the test in mind, right, or formally written down before you start writing your code in the first place is always a good practice, right? Because whenever you are writing a code, let's say you are writing a function to compute something, you should have a clear picture of what the output is going to look like, so that when you finally see the output, you know whether it's correct or not. And as long as you have some kind of an idea like that, it should be possible to write a test that tells you whether or not you are on the right track. So an important sort of variant of this is that once you write a test for a function, you should never fail those tests even after subsequent modifications to your entire code base. This is sometimes also called regression, right? You want to ensure that there are no regressions to older behavior or wrong behavior, right? A regression is considered sort of falling back towards wrong behavior, and you don't want to have any kind of breakage in the test coverage. Usually because of this, what happens is that for any reasonably complex software system, you end up with a large test suite, right? There is a large collection of small tests. Each test by itself should run extremely fast, right, and should be easy to set up, run, and in fact understand what exactly it's doing. And the reason it has to be fast is because typically we want to automate this process. We want it such that every time there is a sort of change in some parts of the code, I would then just run the entire suite of tests and say, yeah, every single test is now passing, right? The normal way by which this is done in software engineering projects is actually to set up an automated system which says that every time, let's say that somebody checks in a set of changes into your version control repository, possibly on Git, using Git, or on GitHub or something like that, all tests should then get run. Now you may also not want this to run every single time, but it is very common to have a scenario where every night, for example, you trigger the entire set of tests to be run on the system, right? And this is because every day people would make a certain set of changes, they would push in their changes into the system, and you want to ensure that next day when people come back to work, it's very clear whether any of the tests that were previously passing broke due to any changes that were pushed in the previous day, right? And having some kind of automated testing like this actually makes catching these kind of issues early much easier to do. An example of code could be something like this. Let's say that you are doing a temperature monitoring system and you have a couple of functions. One of them is basically to read the temperature and another one is to set an alarm, right? Now in this case, I'm not even showing what the functionality is. In fact, from what you can see over here, read temperature seems to be a sort of standard function. Set alarm once again would have something related to the temperature that has been read and then needs to do something. right? Now if I wanted to test functionality, then I'm not probably going to test for this function, the read temperature by itself. What I would have is that I would need to be, and the actual read temperature is probably going to read out a value which is coming from a sensor, right? Similarly, set alarm might actually have as its behavior that it needs to go and possibly turn on a light or an LED or something of that sort, right? Testing something like that in hardware becomes difficult to do. So instead what I can do is declare a couple of other helper functions which are called mock functions in this case. And the purpose of the mock function is basically to say that if I call read temperature while doing testing, use this function, the mock read temperature instead. And the mock read temperature has a much simpler behavior, it just basically returns a known value. And the mock set alarm will probably just set the alarm to a known state and return the value to you, or just return in this case, right? Now why is that useful? Because when I am running my tests, I don't have the ability to actually go in there and read from a register. I may not actually be running on hardware, I may be running a simulation of what happens when this function is called in the context of a larger overall system that I am putting together. Okay. Now what is done therefore in practice is that I can actually take the read temperature function, and remember that in C I still have the ability of referring to a function using a function pointer instead, right? So if I actually had read temperature as a function pointer, then I could say that when I was running my tests, I can basically make that function pointer point to the mock read temperature. But when I am running the actual system, I would make the function pointer point to the actual read temperature, which would read from the register, right? Now you might argue that that means that the wrong read temperature is being run, but that's okay. I am not testing the read temperature or the set alarm function by itself. I am testing what happens when those functions are executed and some other condition or some other part of my program needs to run, right? So I could, for example, have a test temperature below threshold where I use a mock that will return a low temperature and use that in order to find out how the system would behave when I actually gave it a low temperature. So mock functions, in other words, are used in order to replace the actual functions that are going to be executed or actual data on which you are going to run with some kind of a mock-up or some kind of fake data or functionality which is good enough to test whatever it is that you are interested in evaluating. So just to dig a bit deeper, right, unit testing in other words involves verifying that individual units of code such as individual functions or perhaps modules in some cases behave as expected when isolated from the rest of the system, right. So unit tests in other words are in some sense isolation tests. They also say that that particular function should be checked by itself without having to depend on the rest of the system being available. And an example could be where, let's say that you know that there is an A to D converter, it could be the temperature sensor, right, and you want to check that it returns the correct value for different input voltages. Now the example that I showed you over there was of course something where the mock read temperature would just return a fixed value. Another way could be that perhaps I have a function that takes a number as input, converts it into a floating point value corresponding to an actual temperature and then returns that value. And I could test that by then feeding in different possible readings that could have come from the register that I read and seeing whether it converts all of them properly. Make sure there is no overflow, make sure that the range is correct, make sure that the linearity of my conversion function is correct and so on. So the main point is, in this case we are focusing on a single self-contained function, right, one which just does the A to D conversion out here and doesn't depend on other parts of my program. Integration testing is usually when you have multiple units of code that you are now trying to make them work together, right. So you have different unit functions that you have tested individually, you are now trying to integrate them together. An example could be something where you have a DC motor, you have written a PID, proportional integral derivative. Again, we have not looked at this as part of this course as such, but it's a common kind of control mechanism used for controlling motors in embedded systems, right? Which means that there is some kind of an algorithm that is actually running inside this controller. There is also something else that actually controls the DC motor, takes the value generated by the PID algorithm and feeds it out to the motor. Then there will be some sensor that actually checks the speed of the motor and gives it as feedback. So you have multiple different functions out here. You want to integrate all of them together and have some kind of a test that basically tells you that the overall function is working correctly. System level testing takes the entire thing one level higher. It basically says I'm building the entire thing. You have the whole robot out here, right? You have a robotic arm using multiple sensors and actuators, and your system level tests would probably be that, okay, if I have a particular ball in a certain location and I want the robotic arm to correctly go and pick it up if it has got a certain class of input, right? Or maybe the video camera above it is telling it where the presence of the ball is. You could have more complicated tests of that sort, right? By definition, a system level test is significantly more complex than a unit level test. It could take longer to run. It is also assumed that you are not running these on a daily sort of continuous basis, right? System level tests are things that you need to define in terms of the overall functionality of the system, but they will also typically be run at a less periodic granularity than the unit level tests. One thing that's important to understand is that embedded systems are always targeted at an end user, which means that the acceptance from the user is a very important part of what you are looking at, right? Typically, an embedded system is not something that you are designing just for your own private use. You are designing it for someone else, and that person is the end user. They are stakeholders, in other words, they are customers potentially of whatever it is that you are trying to build, which means that you could actually have a more complicated kind of testing. The customer might actually be interested in saying, okay, does the robotic arm actually pick up a soap from a particular place, put it into the correct package, fit them all in properly, and then close the package, right? That is their particular use case. There might be another customer who wants to use a robotic arm for something else, right? But the acceptance testing would basically be required, and that would directly need input from the end user of the system. And especially in the context of embedded systems, there is so-called hardware in the loop testing, right? Where for all that we have done so far, a lot of the tests could be just software, they can be automated, but embedded systems ultimately are most likely dealing with the real world. You could, for example, have a traffic light system where you either want to simulate real world traffic patterns, but even a simulation like that is not actually hardware in the loop. You actually want it to run with potential inputs that are coming directly from the system. Or you might have a motor control where rather than having a model of the motor, you actually put the motor into the system, feed the PID control output directly to it, get the sensors to give you back data from the corresponding to the speed of the motor, and therefore the actual hardware that's present in this testing loop is ensuring that the inputs and the conditions under which you are testing are actually realistic, and you don't have to worry about whether your mock functions have captured the real scenario accurately or not. So in other words, this is particularly important for embedded systems, even more than for generic kinds of software. There are a lot of best practices, as you can imagine, and I'm sort of going to leave it with just a brief sort of review of those rather than going into detail on them. General guidelines, the first thing of course is you need to understand the system requirements, right? Not just the individual functions that have been assigned for people to develop. You need to understand in what context you are developing such a system and where potential problems could arise from there. Unit tests by definition pretty much are done in isolation. You need to isolate the individual components of your overall design and be able to test them out by themselves. As far as possible, try and think of real world scenarios that actually reflect the working conditions under which your system is expected to work so that your tests are realistic. and needless to say have multiple test cases, right? Just having one test and saying yes the system works versus having many tests and saying okay now I'm reasonably confident it works at least under these conditions is good. But that's just having a large number of tests is not sufficient. You need to have something which sort of tests at the system level. In other words, if you are trying to test whether a function to square a number works, it's no use just giving it 1, 2, 3, 4, 5 and checking whether it gave the correct values. You need to start giving it large enough values that could potentially break it, maybe cause an integer overflow or some other kind of wrong behavior, and see how does it behave under those conditions. At least is it behaving as expected? It's entirely possible that yes integer overflow happens and this is the only thing that you can do, but you need to at least be clear that if such a thing happens, what is your program or your function supposed to do. And one of the most important things over here is you should be able to automate these tests, because otherwise, especially at the unit testing level, without automation it becomes more or less useless, right? I mean you can't really manually go in and run a large number of unit tests on a regular basis unless you have some way of actually automating and saying okay this is one command, it will go out and run all of these tests and report back to you how many passed and how many failed. The purpose of unit tests is kind of lost. Now specifically in the context of embedded systems, there are certain kinds of tests that may not generally apply for other kinds of software systems. One of them would be the fact that you are dealing with real world sensor data, right? Embedded systems could be applied in specific kinds of safety critical scenarios, which means that you need to have some kind of tests that actually check for behavior under extreme conditions to know what would happen if something actually went wrong and what are the, how does the system fail essentially, right? There are so called fail safe mechanisms which basically say that even if something goes wrong there should be some way of safely shutting down the system without for example causing a nuclear explosion that basically renders the entire neighborhood uninhabitable, right? And another thing that could happen in the context of embedded systems would be related to power consumption, right? Do you have sort of power constraints on your system, and if so is there a way by which you can test that your system is never going to violate those kind of constraints? All of these are more related specifically to the domain of embedded systems. But there's one rule more than anything else that's sort of important and which we sometimes tend to get carried away when you look at unit testing and so on and try and add more and more complicated tests. Probably the most important rule from the point of any kind of system design is keep it simple, right? And what I mean by that is try and have it in such a way that your test should be understandable. It should be possible to explain clearly why a given set of tests is needed and why, if you have chosen not to test something else, why it is not really relevant to your system. Although we generally try to say have multiple tests, in general having too many tests is also a bad thing, because it means that you are sort of relying on just having a large number of tests and assuming that just by having a large number of tests somehow that is proving something, whereas in reality it's not. What is actually happening is that you might have missed out on critical corner cases, and sort of thinking about it and coming up with the right kind of tests is usually more important than just having a very large number of tests.